Swayam Prabha. Digital India. Educated India.
Welcome to fourth lecture of video course on tribology. We are going to discuss on how to estimate friction with reliability, providing results as we get from experiments. In previous lecture, we discussed three theories: adhesion, then flowing by conical theory, and flowing by spherical aspirity theory. If I summarize those three theories, what we get in adhesion, generally two surfaces get welded under pressure. That is why we call this mode of friction as adhesion friction. In second and third, it is a displacement of surface, displacement of material due to the asperities of hard material. And we develop mathematical relations. For adhesion, we say it is a ratio of shear strength to the hardness. Lower the shear strength of material, higher the higher hardness will provide lower coefficient of friction. However, we discuss also what are the drawbacks. As I mentioned that if same material has been used against a number of pairs, this theory will provide same coefficient of friction for all material pair, which is not right. Then we develop mathematical relation for friction by deformation, or we say the conical aspirity deformation caused by conical aspirity, and we develop the relation as a 2 by pi into cot theta. It is a very sensitive relation, and here the theta is a half angle of cone. If I simplify, say the 2 divided by pi is equal to 0.06366 or nearby 0.64, and expressed in terms of depth of penetration and radius of the cone at interface, then I will get a relation something like that 0.64 into h divided by r. This is a more or less same relation which we developed for spherical asperities. You see, in the mu d for spherical aspirity was a 0.6 square root of h by r. R is the radius of spherical aspirity. So, there is a lot of symmetry between the second relation and third relation. Only thing is that in second it is much more sensitive, effect of h is much more dominant compared to effect which is shown in expression third, deformation by aspirity, spherical aspirity. In totality, all these three expressions are not providing very good results. That is why the Borden and Tabor, who developed theory based on adhesion initially, try to modify it, assuming that there is a possibility of this area to be extended or grow as we apply tangential force. In other words, friction force is going to increase area of contact. That was their hypothesis, and then they try to give some explanation, some derivation or mathematical derivation. To elaborate, I am just taking these two pairs in contact, assuming both the pair are rough. They come into contact only at the asperities. You can see there is an area of contact. Some force has been applied, a normal force has been applied, some tensional force has been applied. Force equilibrium is shown in this element. Now, if I take a help of principal stresses or use a solid mechanics to drive the relation, what we can get principal stress 1, principal stress 2 is equal to average stress, stress in x direction and stress in y direction, plus minus, plus will be for sigma 1 and minus will be for sigma 2. Then this is the average plus this is a shear strength. If I simplify it, you say that assume there is a normal load only in y direction and x direction there is no force, then sigma x will be 0, sigma y will be the normal force divided by area or projected area, while shear stress will be friction force divided by contact area. These are the simple expression. Difficult expression can be achieved, but we want to find out initially or with this approximate relation which can give some results close to the experiment results. Now, if I use a expression sigma 1 with a plus sign and sigma 2 with a minus sign, I will be getting relation something like this, and we know very well if we subtract expression 2 from expression 1, I will be getting the difference in principal stress, and that should be the minimum yield strength of the material which is supporting that kind of load or supporting the W load. So, we subtract and we get expression something like this. You can see there is a normal force divided by 2 plus tangential force, and this is sigma 1 minus sigma 2, which I am saying that this should be equal to, or minimum value of yield strength should be equal to this. It can be more than that, but minimum value should be like this. So, we can substitute those values. Sigma y is equal to sigma 1 minus sigma 2, and if I use a shear strength approximation, we say that shear strength is generally 50% of yield strength, depend on the which theory I am using, which maximum shear stress or Tresca theory I am using. If the Tresca theory, then it will be the 0.577 sigma y, while one might say it will be 0.7577, while in case of Tresca theory it will be 50% of yield strength. To substitute these values, what we get expression something like this as the area or elemental area into shear strength of material, expression for normal force or 50% of normal force square of that, and then tangential force. For present case, we are assuming the normal load is not going to change, it remains same. Material period is not going to change, it remains same. What is the meaning of that? This W and tau y is not going to change. So, this indicates if we increase value of F, value of A need to be increased to get the reliable results, or we can say friction force is a function of area of contact. Friction force is function of area of contact. With increase in a friction force, area of contact will continuously increase, but there will be a limiting value. Beyond certain area, it cannot be increased further. We can say the limiting value of A is equal to A max, right. So, it will reach to one level, and to differentiate between the shear strengths, you can say that let us take a shear strength of interface and represent as a tau I, where friction force or we say one surface will be getting separated from other surface. There will be a breakage of contacts or breakage of cold welds which were made during the normal load or initial loads, then only the sliding will start. So, we can represent F as a tau I shear strength of interface into area, that is a limiting area A max. We substitute those values, what we get? F limiting or F friction force is equal to tau I into area, maximum area which can be developed, which can be grown to the maximum value. And if I substitute these values in this expression which we derived in previous slide, what we get something like this: A max into tau I square, because area is continuously increasing. This normal force will remain same, or term which contain the normal force will be same. And last expression is a friction force. We can rearrange, we can find out the value of W from this. What will be maximum value which we can be applying, or which can be applied on this interface. And we know coefficient of friction can be represented as friction force divided by normal load. I can substitute this tau I into A max over here, and W after rearranging can be represented in this form: 2 square root of tau y square minus tau I square in bracket and multiply with A max square. A max and this A max will cancel out, and what we will get an expression in terms of shear strengths. Shear strength of the interface, shear strength of soft material. That is a difference. We are saying that there is a difference. If interface is getting fractured at the value of shear strength of material, then coefficient of friction will be very, very high. However, if the shear strength of the interface is very low, irrespective of what is the value of the tau I, the coefficient of friction will be lesser, and this is the reason why we provide lubricant. If we provide lubricant at the interface, shear strength of interface will be almost negligible compared to the solid material strength. Just to get a feel of that, we did some calculations. We said, let us take an example that tau I by tau y is can be given in some ratio. Let us take a tau I divided by tau y is 1% or 0.01. If that is the case, if interface shear strength is just 1% of soft material shear strength, coefficient of friction is almost negligible. It is a 0.005. If we increase that to the 10%, we say interface is made in such a manner, interface shear strength is 10% of soft material shear strength, then coefficient of friction increases also 10 times. Earlier it was 0.005, now here it is a 0.05. We further increase to 20%, what we get? It is almost double. From 10 to 20 is almost getting double, from 0.05 to the 0.1. Similarly, we can do more number of iterations and we come to the result. See, when it is a 99%, interface shear strength is 99% of the bulk shear strength of soft material, coefficient of friction is predicted as a 3.5. And this is very close to the what we got the result from experiments. Experimental result shows that there are two soft materials are used, their interface shear strength will be very high, almost equal to the one of the weak material shear strength, and coefficient of friction can be very high, maybe 3 to 4 or 3.5 what we are getting from here, right. So, we can interpret our result, this tabular result, in such a manner the ratio of shear strengths decide mu. It is not an absolute value of tau I or tau y decide the what will be the coefficient of friction, what will be the coefficient of friction due to adhesion, but it is a ratio which decides. If a strength interface is strong and bulk material is also strong, we will get a one kind of shear strength. If the interface is weak in the sense it is having a cold junction, firm cold junction, then again the shear strength of the material will be comparable to interface, again the coefficient of friction will be very high. However, if I say in terms of a strong interface, strong in the terms it is related to material and is attached firmly to the material, one layer which is firmly attached to the parent material, in that case there is a possibility of low interface shear strength. To elaborate that, let us take one picture. You can see this is one of the metal surface which has a work hardened surface, then oxide layer due to availability of oxygen in environment, then some absorption, some contamination, and these layers are very, very thin. We are talking about the 30 angstrom, talking about 100 angstrom, and in this case maybe roughly 10 micron. So, when the material is a virgin, the behavior of the material will be different. If it is a work hardened, maybe say 10 micron work hardening layer on that, then its interface shear strength will change, or interaction with other material will change. In that next one is that oxide layer. If there is oxide layer, maybe say even 100 angstrom, that can change the interface shear strength. In short, this layer decide the behavior of tribose surfaces. If all 3 layers or all 4 layers are removed from the surface, then we will be getting very high coefficient of friction, and in fact it happens in the soft materials like a gold, indium. They do not get those many layers. However, in steel, chromium, we can get a good number of layers, good oxide layers on the top of the surface, and they prevent adhesion. They make interface weak shear interface, or shear strength of interface is almost negligible in those cases. That is why we get a low coefficient of friction. However, if we remove these layers, coefficient of friction will increase. We can do this kind of experiment in a laboratory when the shaft is machined, and if immediately we try to run at the high speed, we will find there is a high coefficient of friction and complete welding on that. However, if we grease it and then run in the bearing or a subsurface, we will find coefficient of friction is much lesser. Reason being, the lubricant layer or grease layer has a thin or coat a thin layer on the shaft surface and reduce interface shear strength. That interface shear strength compared to the bulk shear strength of a steel shaft, and then we will get a good result. And in this case, we believe that if the surface roughness of the other surface, maybe say there are 2 surfaces and one surface has a coating this kind of layers, another surface has a high hardness with high surface roughness, this may damage the protective layer. That means, if surface roughness is very high, there is a possibility of damaging those protective layers and increasing the coefficient of friction in those cases. We somehow do not want that kind of thing. That is why we are always preferring low surface roughness of the surface as well as some protective layer. In the short, adhesion theory, or which was derived using the junction growth, is applicable along with asperitic contact, where the asperities need to be much lesser in size and height as well as in hardness, so that they do not create cavities or plowing effect on the soft surface. I can think over some possible situations. So that assume the metal is weak and oxide layer is weak. Here when we are talking about a weak oxide layer, it is not an absolute sense, it is only relative sense. This layer attached with the ductile material, and strength of that layer over ductile material is low. You are not talking any other thing that is the only attachment or adhesion to the parent material to this ductile material is weak. That means, it will be simply removed or abrupted or delaminated if there is some surface roughness or some tangential force on applied by some harder surface. So, what we are able to say from that, this film which is made of the weak oxide film, it can be easily broken, because in bonding to the parent material is much weaker, and this kind of material with weak oxide layer will undergo rapid junction growth, result very high value of mu, high coefficient of friction. Couple of example on which belong to this category are indium, gold. Gold to gold, we found the coefficient of friction very high. Indium to indium, we found the coefficient of friction very high. Even if the indium versus gold will be having a high coefficient of friction. We can take another example. We assume that there is a weak metal, the shear strength is low, but there is a strong oxide. Here, a strong oxide is adhesion of oxide layer on the material, exclusively that. In that case, what will happen initially? There will be coefficient of friction will be very low, or maybe say reasonably low value. After some time, if the interface or rupture interface between the weak metal and oxide layer. We are not talking tribo pair, we are talking about the metal and oxide layer. If that is ruptured, then there will be transition, and that due to this transition coefficient of friction will increase drastically. Examples are in this case are the copper and iron. We have found many times oxide layer on a iron, and if it is deformed excessively, it will be removed from the surface and coefficient of friction will suddenly increase. What we term that as a transition load. And the last, which is the most favorable, is a strong metal and a strong oxide. Both surfaces surface as well as oxide layer are firmly attached. They have a strong bonding, or oxide layer has a strong bonding on metal. In that case, what will happen, irrespective of the loads, because the strength of the bond is very high, all the loads it can sustain, maybe say all the load in this, there is a reasonable extent of a region. It is not going to immediately rupture under slightly higher load or moderate load. Example in for this category are this steel and chromium, where they make a strong bonding with oxide layer or layer which is formed due to environment, due to contamination, that is a strong, or bonding of that oxide layer is strong. If I plot this diagram on the diagram, what we say that this red color line belongs to the first category, that is a weak metal and weak oxide. Coming to the second one, the weak metal and a strong oxide can be plotted something like a blue line. You say that there is a stationary or maybe initially constant coefficient of friction, and then there is a rupture of the layer, and then that is why there is a sudden increase in coefficient of friction. Finally, we say that the green color light, which is most favorable, we accept this is having a combination strong metal and strong oxide. That layer is always appreciated. Whenever we design any tribal pair, we should aim for this kind of layer, so that we can get low coefficient of friction. However, if we want a high coefficient of friction, then we can choose first case, but in that case wear rate will be also very high, and then we need to provide appropriate action or appropriate tools to get a solution. Now, this is a note finally coming on this slide is both junction growth and plowing effects. Here I use the word 2 and 3. 2 and 3, that means plowing is generally occurred due to the 2 body and 3 body. When we are talking about 2 body is something asperities which are firmly attached to the surfaces, and only asperities and asperities are coming into contact. When you are talking about the 3 body plowing, in that case we are assuming there are some debris at the interface, and that is creating some sort of plowing effect. Let us take an example of the sand. If sand comes between the 2 soft materials, then the sand particle will start plowing or start digging either material 1 and material 2. So, that will cause some friction losses. We are talking about that the plowing due to 3 body, and when we are talking only asperities is the 2 body plowing effect. They play important role, and depend on the situation, either of this mechanism will play dominated role. If there is no lubricant, extra smooth surface, high cohesion or high adhesion between the material pair, or high cohesion between the similar pairs, then coefficient of friction due to adhesion will be very high, and the plowing will be almost negligible. However, if there is a partial lubricant, adhesion component can be reduced to almost negligible level, but because of the surface softness there will be some plowing effect, and if there is a clear separation between 2 surfaces, then the plowing as well as adhesion will be negligible, and then that can be treated as a full film lubrication, which is not a topic in this category. We will be discussing that topic in later when we start fluid film lubrication mechanism. Now, how to reduce the junction growth? I have noted down few points, few suggestions. Not necessary everything will work in one situation, but one of the suggestions will work to reduce the junction growth. Say if you want to really reduce the junction growth, do not think about the dry lubrication, provide some sort of lubricant, either powder lubrication, solid lubrication, semi-solid lubrication or liquid lubrication, which reduces the interface shear strength between two surfaces is fine. It is something like when we play carom board, we use a powder lubrication, we provide a powder form, a similar kind of action which has a loose strength with low shear strength, that will work on this. And there is a possibility to choose appropriate material. We say that when you choose low soft material as a third material, then it may provide as a low shear strength, and that may work. That is why many times we are using a molybdenum disulfide between the two contacting surfaces, which has a very low shear strength. It can sustain, molybdenum disulfide can sustain high compressive load, but shear strength is negligible. Shear planes will simply move under some load. So, that is appreciated. Next suggestion is that never use the same metal or metal which have a similar kind of chemical structure, or they have a high molecular attraction. To explain this, we can take example of copper. The coefficient of friction is a 1.0. Reason being, if they are not this material pair are not oxidized and they are virgin materials, they will come in a contact, they will form cold junction. Under shear force, the junction will grow, and finally a limiting shear strength will come, which is by and large equal to bulk material of copper or shear strength of copper itself. Coming to the second pair is the aluminum with the low carbon steel. Again, in this case both material are soft materials, and when they make a junction, that junction will grow under tangential load. Coefficient of friction in that case will turn out to be 0.8. However, silver and the low carbon steel is a good example here. Their shear strength or their interface shear strength is relatively low, and that is why they give low coefficient of friction. Sometimes we play with the ductility also. We say they use this low ductile material which can be easily ruptured. Apply slight force on that, it can be easily ruptured at the interface, and that will provide a low coefficient of friction. However, there is a problem. If that rupture happens to be very rapid or it deteriorates the surface softness, then we should not use this kind of suggestion. We should use some sort of lubricant, or many times we use water to lubricate the surfaces. And there are some observation which we got in the lab is that coefficient of friction not necessary remains same throughout the time. It's from the start of operation to the end of operation. Of course, we have already explained in the previous lecture what is the kinetic coefficient of friction and what is the static coefficient of friction. However, there is a slight change in the terminology. Many times in the right and then book you find steady coefficient of friction. Steady coefficient of friction is equal to the kinetic coefficient of friction. What is the meaning of that? At the start there will be some coefficient of friction, but that will change. That will be different than steady coefficient of friction or kinetic coefficient of friction. So, there is a slight change in terminology, a slight confusion in terminology. When we say static coefficient of friction, that is a start before running in time. When we say steady coefficient of friction, that is a kinetic coefficient of friction. It is going to happen during the working life of a component. Running in time we are not counting, and remaining whatever the number of hours which that tribo pair can sustain, that will show a steady nature of coefficient of friction. We are talking about that. However, there is a possibility of change in coefficient of friction even under steady running condition. What do we say that when we are bringing two new surfaces, just fresh surfaces, they will there will be higher flowing effect at the start and relatively low adhesion. If the surfaces are unpolished, the surfaces are very having a super finish, they are perfectly polished, then possibility is that there will be high adhesion and low blowing effect. But we are talking about the normal manufacturing surfaces which have a relatively high roughness. In that case, blowing effect will be very high initially compared to the adhesion. And if this process continues, there will be some rupture, some breakage of the asperities. Due to that, there will be a reduction in blowing effect, or coefficient of blowing will decrease, but this due to this there will be increase in coefficient of friction due to adhesion. More and more asperities are keep coming in contact due to rupture, or we say the rupture of high level or high magnitude asperities. There is another possibilities, these wear debris come between the interface, and that will increase the coefficient of friction. So, if I start again, you say that initially two body flowing effect will be there. Subsequent to that, there will be rupture of asperities, where debris will be at the interface. There will be adhesion or increase in adhesion coefficient of friction, because more and more asperities are coming into contact. So, there will be overall dynamics, few asperities will be ruptured. So, blowing effect should reduce, few asperities more number of asperities will come in a contact, then adhesion coefficient will increase, and few debris will come at the interface, then coefficient of friction should increase. That way there is a transition behavior if I try to plot it. So, blowing effect initially I am showing going down with a rupture of asperities. After that, it is reaching to the one dynamic situation, by and large giving constant coefficient of friction. Here, even though there is a possibility of further rupture of asperities, but those asperities there is a possibility that they will remain as a debris between the interface. So, 2 body and 3 body overall will come to the equilibrium, will give a steady value of coefficient of friction. Coming to the second one, there is a red color line. This red color line shows that adhesion will increase with the rupture of asperities. More asperities will come into contact, and there will be more and more junction formation. But junction formation and junction rupture will be a continuous process. So, finally, they have to come to one equilibrium position. That is why blue color line and red color line, when we average, will give us some steady behavior. However, there is a problem. If situations are not under control, speed is increasing suddenly, load is increasing suddenly, then any of this line can terminate the component life. Any of this line will end the life of the component, or causes excess wear, very high coefficient of friction. So, that is why we are keeping this as imaginary lines. They depend on the load condition, they depend on the temperature, they depend on whether the lubricant layer was initially there and got was removed from the surface because of the starvation, because of pump failure, because of misalignment, or some other reasons. So, there is a possibility of this kind of hypothetical lines. It can be maybe say similar 2 pairs. One pair can show life is starting, coefficient of friction is decreasing, reaching a steady state condition, and then again coefficient of friction increasing. Other component or similar component, similar material pair, in another condition it can show reaching to this condition, moving to straight condition, and finally ends with this line. It depends on environmental condition, this line will be selected, or there is a possibility of external life, or many times we get the infinite life. That is also a possibility of infinite life. It will show coefficient of friction as a steady value throughout its life. There is a possibility. We have been discussing about the sliding friction, but there is another option with what we call the rolling friction. From history, we know very well that rolling friction is always preferred compared to sliding friction. What we say, as far as possible, avoid sliding friction, bring rolling friction into picture. We have heard about sliding bearings have been replaced with the small rollers. So, the coefficient of friction is steady and gives reliably low value. And we can say coefficient of friction due to rolling, that is represented here with a mu r, is generally smaller than that caused by the sliding action. This is always desirable for machines. If I have choice, I will prefer rolling friction compared to sliding friction, if friction reduction is my main aim. So, that it can be defined as a ratio of forces also, or it can be defined as a ratio of moments also. In this case, we are assuming there is a ratio of force, the force required to maintain steady rolling divided by the load which is applied on the roller or tribopia. One of the interesting thing is that rolling coefficient or rolling friction coefficient depends on the hardness. So, there is a symmetry, there is a similar behavior. Sliding friction also depends on a hardness. Higher the hardness, by and large, higher the hardness, coefficient of friction will be lesser. Same behavior is adopted or opted by the rolling coefficient of friction also. Higher the hardness, lesser will be the coefficient of friction. And reason behind this is that if there is a high hardness, there is a lesser chance of obviously the magnitude of deformation will be lesser, depth of penetration will be lesser in that case. So, if the depth of penetration is lesser, there is a chances that material will show lesser hysteresis. If I think from the hysteresis loop point of view, from the loading and unloading point of view, if material have a hysteresis behavior, it does not regain its position without losing energy, then coefficient of friction will be high. However, if it gains same position without losing much energy, then coefficient of friction will be lesser. So, we have a couple of examples. We say that if we start with a hard steel roller or hard steel ball also, then if it is roll or on the flat surface or in convex or concave surface, the coefficient of friction may be in the range of 0.01 to 0.001. We are using the word here smooth, that means surface roughness is not accounted. If the surface roughness accounts, then there will be surely some sliding on that, it will not be perfect rolling. And we are talking about the hardness. If the surface is hard, if the surface is turned out to be soft, then there will be excessive deformation, and due to that excessive deformation there will be loss due to hysteresis, and that will be counted as coefficient of friction. That is why in a second line it is written a roller or a sphere with the ball over here made of the soft material, when rolled over other soft surface, it generates high level of coefficient of friction. Rolling friction will be high, rolling resistance will be high in that case, if the material pair is soft and soft. If the hard material is rolling over the hard material, deformation will be lower, in that case coefficient of friction will also be lower. If I see the all mechanisms, I can divide this coefficient of friction due to the 4 mechanisms. We say that even under rolling condition there is a possibility of micro slip between the material pair. There is a possibility of elastic deformation, there is a possibility of plastic deformation, and if there is a thermal change or behavior change due to the temperature, then again there will be coefficient of friction. So, 4 mechanism, but we are assuming for timing that we are not going in the plastic domain. The plastic domain coefficient of friction is neglected in this case, and there is a very low chance of micro slip, very low chance of excessive heating. So, we will consider only an elastic case. Suppose elastic itself is going to give a coefficient of friction. So, to demonstrate that, there is a diagram which shows that the roller rolling in clockwise direction, when it start rolling, what it will be, what happened to the material, it will be going to the some pressure, and if this is a rubber material, then there will be excessive deformation of surface. Now, what will happen if the surface is not straight, it is going under deformation, that means point contact is converting getting converted to the area contact, or line contact is getting converted to the area contact. So, there is a substantial area of area contact in that introduce some sort of micro slip and as well as hysteresis losses. In this case, it is shown when it is relieved at the back end, it is recovered energy whatever has been given initially, it has been recovered at the back side, but due to rubber which has heat dissipation capabilities or heat absorption and capabilities or say energy absorption capabilities, in that case energy will not be given back completely, some portion will be lost, and that will cause a coefficient of friction. Now, if I think from the lubricant point of view, we are able to say the use of lubricant does not help to reduce rolling friction. In this case, even when you are providing a lubricant, it does not help much. There is no adhesion, it is only the deformation, and we know very well liquid by and large, if it is a very thin lubricant layer, if it is not completely separating, then it will not change coefficient of friction, it will not absorb any deformation, and the load which you are talking in the rolling contact is generally very high compared to sliding contact. In that case, lubricant layer really does not play much role if only elastic deformation is causing coefficient of friction. So, this is what we will mention here: hard steel rolling over soft rubber, and it rolls along, the ball displays rubber elastoplastically around. If I assume only elastic deformation, then it will regain perfect shape. However, assume elastoplastic, then there will be permanent deformation on the rubber material. For simplicity, we generally assume the load, applied load is much lower than which can cause a plastic deformation. Now, depends on behavior of the material, whether it is a bouncy rubber. If it is a bouncy rubber, it is not a sagging rubber, it is not going under plastic deformation, but we say that our applied load in such a manner, it retains the bounciness of the rubber, then coefficient of friction will be less. However, the soggy rubber which does not have good molecular bonding, and when it is subjected to deformation, it gets that shape, and if it is getting that shape, the coefficient of friction will be high, there will not be energy returned back to the surface. So, we can say that deformation of material will decide the magnitude of rolling friction. Where the coefficient of friction will be high, coefficient of friction will be low, that can be decided by the material behavior. If the material is made of the good rubber, or we say that rubber is made of the good ingredients, in that case coefficient of friction will be slightly lower compared to the simple betadine rubbers. And again the line is coming over here, we say lubricant cannot reduce deformation of the surface, therefore, lubricant have very little effect on the rolling friction. It will not be able to reduce coefficient of friction substantially. That is a case. Now, we have a number of expressions for the rolling element bearings, or which define what will be the rolling friction. We will be discussing those detailed expression when we deliver lecture, or we discuss about the rolling element behaviors or rolling element bearing design and selection of the rolling element bearings. That time we will be discussing those detailed expression. However, I am just providing two simple examples on this slide. Is that ball bearing, we are assuming they are made of the hard steel, they are made intentionally with the hard steel. So, the deformation is negligible, it can really roll, or roll to sliding ratio is very high. Now, second assumption here, we are saying that load which is applied is within elastic limits, it is not high enough to produce any plastic flow of the ball, there is no plastic deformation. What will happen in that case? If this is a situation which we are providing, then hysteresis losses will be very low, generally lesser than 1%. So, what will happen? Most of the cases the coefficient of friction will be 0.01 to 0.001. However, we know the rolling element bearings come with the cages, separators. We provide cage to separate the two rolling elements. Reason being, if the one rolling element is disturbing other rolling element, what we call the fully complement bearings, load carrying capacity will increase, but there will be chances of more friction due to the rolling between two surface itself. It will start retarding each other motion, and then will create a high coefficient of friction at the interface. However, to get a more uniform loading in that case, we say that to keep separation between the rolling element, we provide a separator or cages, and they have a much more area of contact with the rolling element that is causing higher coefficient of friction in rolling element bearings. When sliding happens between the cage and the ball, it will not be perfectly rolling, it will not be pure rolling, it will be rolling come sliding, then coefficient of friction naturally will be higher, and if we do not provide any lubricant, then coefficient of friction will be really high, the 0.2 to 0.3. Here we can say rolling lubricant is playing a role, because there is a sliding between the cage and rolling element. Providing lubricant has a meaning. It is meaningful to reduce the coefficient of friction due to sliding, but rolling lubricant otherwise cannot reduce the coefficient of friction due to perfect rolling which is happening due to the elastic deformation and regaining. So, the deformation, only the rolling element play the deformation, then lubricant cannot be used, or we say that even if it is used, it is going to create some churning loss. It will be on the negative side, it will not give any benefit to us, but it will give only drawbacks to us. First is the high cost of the lubricant, and again churning losses, and then displacing from the contacting pair, which will happens its own. That means, there will not be very clean surface, lubricant cost, as well as churning losses, so high friction losses. So, providing lubricant in the rolling elements where there is only elastic deformation and pure rolling will cause more problem compared to providing no lubricant or under deforming them under no lubrication conditions. So, we can say in short, whenever we are choosing lubricant, we need to see what kind of deformation mechanisms, or whether the rolling or sliding is happening. If you are able to quantify sliding ratio, if you are able to say yes, sliding is 30% or sliding is 50%, then there is a meaning to provide lubricant, otherwise not. So, this is generally stated, because otherwise when we see the definition of the friction, we say that we require a third substance to reduce coefficient of friction, while in this case third substance will create a more coefficient of friction. So, providing more lubricant in that situation will be more problematic. So, we need to avoid that kind of situations. So, when we compare rolling element, rolling friction and sliding friction, again I can say that we should always vote for the rolling friction as far as possible. However, there is a possibility of high stress concentration due to the rolling action, which requires a special treatment of the material. Maybe many times it turn out to be costly compared to the simple sliding pair. Sliding pair will be economic, and we require a short life, or we require we are not caring about the friction loss or wear loss, we can go ahead with the sliding pair. But if we require very high reliability, definite life, definite fatigue life with high reliability, then in that case we should prefer the rolling element, or we should prefer the rolling friction compared to sliding friction. When we discuss the rolling friction, we are adding one more thing, that when we take an example of tire, then we need to see whether the tire is completely filled with air or not. When we drive car, many times due to the lesser filling of the tire, deformation of the tire will be excessive, and that will cause high coefficient of friction, will be losing the petrol consumption, or we say that will be traveling some kilometers per unit liter, that will be lesser than tire having completely filled air, or we say completely filled air. That is why it is this slide shows that in free rolling the tire is deformed and it meets the road surface, but it recovers as it leaves. It is deformed because of the nature of surface. It is a rubber material and is filled with air, so it will deform to some extent, but it will recover. Now, if we use a good tire material which has a low stresses then energy saving will be very high. we say that if there is a negligible slip between the tire and road, then energy loss will not be very large. That is roughly the estimation is given as a coefficient of friction 0.01 to 0.03. However, if the rubber material is made, or we say the tire is made of the rubber material having high hysteresis losses, what will happen in that case? Elastic deformation will be very high, more than what we understand when the coefficient of friction was a 0.01 to 0.03. Then in that case, rolling friction will be larger and power losses will be higher side. So, even when we choose next time the tire for our car, we should choose rubber tire which has lesser hysteresis. However, choosing that kind of tire may create some problem. What we say, when hysteresis losses are lower, is a perfect rolling, then there will be some problem related to the steering of the vehicle. We say that high hysteresis loss by tire increase the controllability. A slight deformation of the tire will help in controllability, will provide the right direction, but if it is a perfect rolling, then in that case we face some steering related problem or a direction related problem. So, there should be a trade off. We should not have perfect rolling, there should be some deformation of the surface, so that we have a good control on our vehicle. So, this is what we say, that controllability means a better gripping of the road during acceleration, deceleration, or when we are taking any turn, that is required. And in addition to that, this deformation provides some sort of comfort. It acts like a spring action, or maybe say that the part of a shock absorber. It does not transmit all road unevenness to the passengers. So, from that angle, from comfort point of view, you can say that some elastic deformation need to be there, or rubber material need to have that kind of deformation. It should not be very rigid, it should not be very solid, otherwise the whole vibration of road, whatever the road condition, will directly get transmitted to the passenger who is sitting inside, and it will not be very good option. So, a balance, to keep a low coefficient of friction, there should be perfect rolling. To give good controllability, good comfort, there should be some elastic deformation, and whenever there is some elastic deformation, surely there will be some additional sliding or micro slip will be there, and coefficient of friction even under rolling due to deformation will be high compared to perfect shape with non-deformating or with a rigid tire coefficient of friction. With this, I am closing today's lecture, and we will be starting with related to friction instability. Friction causes some instability in number of machines. We will be discussing in our next lecture. Thank you.